Hi, I'm Abby, and this is Physics Lab number 3, Black Hole Lab. The purpose of this lab was to determine the mass of the black hole and determine what minimum initial velocity would be required for the ship to not crash into the black hole as it took off from an orbiting planet. The fundamental physics principles used were Newton's second law of motion and Newton's universal law of gravitation. The overall results of this lab showed that the mass of the black hole was around 1.2 times 10 to the 34 kilograms, and that the minimum velocity required was negative 3.4 times 10 to the 7th meters per second in the x direction, and 4.15 times 10 to the 6th meters per second in the y direction. Some important equations that were used in the lab were Newton's second law of motion, which is F net is equal to the change in momentum over change in time, and it's also equal to F net parallel and F net perpendicular. Use the momentum principle, which is momentum equals mass times velocity, the gravitational force equation, the velocity update equation, and the position update equation. In the first part of the experiment, the system was the black hole and the surroundings was the star, and in part 2, the system was the spaceship and the surroundings were the black hole and the star. Here are the initial conditions for part 1 of the lab. Here's the mass of the star, here's the time interval, which is 1 day, and the time for first observation data point, which is starting at time 0. So here I have the code for part 1 of the lab, and it really starts down here with all the initial conditions. And then here I have P initial and P final, which is just mass times velocity. The change in velocity and the change in momentum are just final minus initial. dp dt, self-explanatory, just delta P over delta T. And then, as stated before, F net equals dp dt. Then here for P hat, it's just the vector divided by the magnitude. And the magnitude of this one is the same thing. So it's the change in magnitude over delta T. And here it's just the magnitude of P dt times P hat to get the parallel vector. Then here it's pretty similar. I'm using the parallel, then dp dt perpendicular to, this is just the total force, and then I set it equal to F net here. And then to calculate the mass of the black hole, I just use Newton's gravitational equation of G times mass times big mass over R squared. And then over down here, I have all of the vectors that show the forces, and they're pretty self-explanatory. It says what each of them are in the name. And then when you run the program, this is what it looks like. So you see the sun orbiting the black hole with the arrows pointing. And then when I took the mass of the black hole, I just ran this experiment a couple times and took the average of it. And at the end, you see F net parallel, and F net perpendicular. And then here is the mass of the black hole again. Here are the initial conditions for part 2 of the lab. So we have the mass of the black hole, which is the average of running the experiment in the first part multiple times, and then the initial velocity of the ship in the both x and y direction. And this was found using trial and error to make sure it didn't crash into the black hole, but still got really close to it. So here I have the code for part 2 of the experiment. Here are all the initial conditions, including the mass of the black hole that we found from the first part. Then down here, we have kind of the same thing going on 4 different times. We have the distance from the black hole to the planet, the magnitude of this vector, r hat of this vector, and then the force of the black hole on the planet, and we're just using the gravitational force equation. And we do that same thing 3 more times, just using the different values for each one. Then down here, we use the velocity update formula and position update formula for both the planet and the ship. And then when you run the program, you see that the ship comes this way and it doesn't crash in the black hole, but it still gets really close, and then the planet is just orbiting right there. A possible error from this experiment was that the initial velocity could have been slightly incorrect because I used trial and error to get the spaceship as close to the black hole as possible without crashing into it, but there is a chance that the initial velocities could have been estimated to more decimal places past what I did. So, what does it mean? How is the net force in its parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular components? So actually, F net and the rate of change of momentum are the exact same thing. Here you can see the derivation of F net. You take acceleration, delta V over delta T, you derive delta P, which is just final minus initial, and when you plug them both into the F net equation, velocities cancel out and you get delta P over delta T. So what if, instead of wanting to take a quick look and leave, you decide you want to enter orbit, what initial velocity would your spaceship need to have in order to enter some kind of orbit? So I found that the spaceship's initial velocity should be this, and it's a slightly larger y component and a slightly smaller x component than the initial velocities I found for the first part when it was just orbiting the black hole. And you can see that they have very similar orbits, but they don't crash into each other. And that's it. Bye bye.